Now let us discuss the another sorting technique, which is selection sort. This is again a brute force approach. In the bubble sort, we were fixing up the largest element. In the selection sort, we will be fixing up the smallest element. The procedure that bubble sort followed was comparing the consecutive element, but here we will employ some different mechanism. Let us take the numbers 100, 60, 90, 30, 40 and 50. So let's say these are the elements. To find the smallest element out of the entire set, we can consider that this element is minimum and then compare every other element of the set with the minimum element. For example, I compare 60 with minimum. This is minimum element for us. 60 is less than minimum, so we will shift the minimum to 60. Now rest of the elements will be compared with 60. So 90 is not less than minimum, so minimum will remain at 60. 30 is less than minimum, so now minimum will shift to this place. And then 40 is not less than minimum, 50 is not less than minimum. So by comparing all the elements in the set, we found that 30 is the smallest element in this set. So let us exchange this 30 with the first element, because in the sorted array, the smallest element should be at the first position. So we are exchanging this element and this element. So 30 and 100 get exchanged. Rest of the elements will remain same. Okay. Now this was our first iteration. Now let us do the second iteration. In the second iteration, I will fix up this element as minimum, and then I will compare every other element of the set with this minimum. First element has already been fixed, so we will not change this position. We will not consider about changing this position. In the sorted array, the smallest element will be at the first position. Now let us compare this element with minimum. Minimum will remain at 60. Compare 100 with 60, no change. Compare 40 with 60. Yes, there will be change, because 40 is less than minimum. Now for 50, if 50 gets compared with 40, no change, because 40 is less and 50 is large. So now we found that 40 is the smallest element. Now exchange this 40 with the second position. So here we have 40 and here we have 60. Okay, so this is the second smallest element. Again, we will do the third iteration accordingly. We fix up this element as minimum and let us compare every other element of the set. So 100 is not smaller than 90, so minimum remains at 90. 60 is small, so minimum shifts to 60. Then 50 is smaller than 60, so minimum now shifts to 50. So now we found the minimum out of these four elements. Let us exchange this with the third element. So position of this element gets fixed. Now we have 30, 40, 50 in the ascending sequence we are finding. Let us do another iteration. In the next iteration, we fix up this element as minimum. Compare rest of the elements with this minimum. 60 gets compared with 50, minimum shifts to 60. 90 gets compared with next minimum, which is 60. So 90 is not smaller than minimum, so minimum remains at 60. Now let us exchange this element with this one. Rest of the elements remain same. Again, do the next iteration. In the next iteration, we will fix up this element as minimum. We will compare rest of the elements with minimum. 90 is less than 100, so minimum will shift to this place. And since we do not have any more element, so let us exchange this minimum with this element. So 90 comes here and 100 is here. So we now remain with only one element. Okay. So what is the element we found 30, 40, 50, 60, 90 and 100 which are in the ascending sequence. So we have performed this sorting with the help of selection sort. Now let us analyze this algorithm. How many comparisons took place in the first iteration? I fixed up this element as minimum, means the first element was fixed as minimum, and then rest of the elements were compared with this element. It means the number of comparisons which took place in the first iteration was 1 less than the total number of elements. So if I have n elements, so number of comparisons took place are n minus 1. In the second iteration, I fixed up second element as minimum and then compared rest of the element with this element. So obviously the number of comparisons will be 1 less than the previous step. Similarly, in the next iteration there will be 1 less comparison. And you see, in the last iteration there is only one comparison. I fix up this element as minimum, compare this with this minimum element. So number of comparisons which are taking place is only 1. So the last iteration I made only one comparison. If I sum it up, so these are the total number of comparisons which is taking place in selection sort. If I reverse this series, 1 plus 2, it can be rewritten as 1 plus 2 plus 3 and so on and so forth up to n minus 1. If I add n to this and subtract n to this, will make no difference. This quantity is summation of first n natural number or the arithmetic progression with the common difference 1, and the number of terms are n. So this can be written as n into n plus 1 by 2 minus n, which is n square by 2 plus n by 2 minus n, which is n square by 2 minus n by 2. So these are the total number of comparisons which are taking place in the selection sort. Now in this selection sort, can we reduce the number of comparisons by any means? Or what we did in the bubble sort, if in any iteration there is no exchange, we said that in the subsequent iteration there will be no exchange. It means the iteration in which I find no exchanges, I declare that my elements are sorted. I do not perform the subsequent iterations. I skip subsequent iterations. But can we do the same here? Let us consider that I have the elements 10, 70, 60, 40 and 50. Let us fix this element as minimum. Now compare rest of the elements with minimum. 70 with this, no, 10 is minimum, so we will not change minimum. 60 with 10, no, minimum will remain at 10. Similarly, if we compare with 40, still minimum is 10. If we compare with 50, still minimum is 10. So minimum did not shift to any place. So if minimum did not shift to any place, it means, can we declare that the rest of the elements are also sorted? No, it is not the case, because here you can see the rest of the elements are in the sequence 70, 60, 40 and 50, which is not in the sorted sequence. So in the bubble sort, we cannot declare that rest of the elements are sorted if in the case there is no exchange with the minimum element. If no exchanges take place in any of the iteration, that does not indicate that rest of the elements are also sorted. It does not indicate that. So in the bubble sort, we cannot skip any of the iteration. We will have to perform all the iterations. So this complexity will remain same irrespective of the nature of the numbers, nature of the inputs given to us. So this is representing the time complexity. There is theta n square. Why we are writing theta? Because there is no best case. All the cases are the same. We will have to perform all the iterations. So that's why we are writing the complexity in the theta notation. So out of n square by 2 and n by 2, n square is dominating factor. So the complexity is written here with respect to this theta n square. Now let us update this in the table for the selection sort. The complexity, time complexity theta n square. We will find out the space complexity also after writing the algorithm. So now let us write the selection sort algorithm. For the selection sort algorithm, you see the name of the algorithm is written in the camel casing form. To make it more readable, we are writing the name of the algorithm as in this camel casing form. Now, first write the first iteration as we did in the bubble sort also. So what happens in the first iteration? We set the first element as minimum. So let us say that the first index element is set as minimum. And now compare rest of the elements, means start comparing the element from second element, means second element, then third element, and so on and so forth up to the last element. So for j equals to 2 to n2. Now let us compare the elements. If a j element is smaller than minimum element, the index of the minimum element is min. So aj gets compared with a min element, and if the aj element is smaller than the minimum element, we switch the minimum to jth position. And once these steps will be performed, means if I will be performing the comparison from every other element of the set, at the end we will have the index of the minimum element, and we will exchange this minimum element with the first element, because we want that the minimum element should be at the first position in the sorted array. So once these all steps will be performed, then I will exchange a1 element with the a min element. So this is the first iteration, and there are n-1 iteration of the similar kind. We have already seen that there will be n-1 iteration. There were 6 elements and we performed n-, you see we had 6 elements and we have performed 5 iterations. If I have n elements, I will perform n-1 iterations. So this entire thing will be enclosed in a loop which is showing the number of iterations. So for I equals to 1 to n-1 to n-1 iteration. Entire thing will be enclosed in this outer loop. And now let us see what changes will be made inside, because in the first iteration we have to make only n-1 comparison. In the second we have to make n-2 comparison, one less than the previous one. In the third iteration I have to make even one less comparison than the previous iteration. So we will do these changes. First change the minimum. In the first iteration, minimum element is set as first element, but in the second iteration it will be set as second element. In the third iteration, minimum will be set as third element. So minimum equals to I. First iteration means I equals to 1, second iteration means I equals to 2, and accordingly the minimum will be initialized to I. And then this comparison will start from the next element. Means if I set first element as minimum, the comparison starts from second element. If I set minimum at second position, then the comparison will start at third position. So this j should start from I plus 1. So here, to make it more clear, let us write this here. So j starts from I plus 1. In any case, it will go up to the last element. So it starts from I plus 1 and goes up to n. And in this exchange, I will exchange minimum element with the ith element. Okay. So this is the selection sort. Let us try to find out what are the elements which are given to us, what are the inputs given to us, and what elements we are taking from our side, what variables we are taking from our side while writing the algorithm. So in this selection sort, A is given and N is given. So we will not consider these in finding out the space complexity. But what are the quantities we took from our side? I, minimum, j, and if we say that we are performing the exchange with the third variable, then an extra variable for exchange. So the total number of extra variables that we took from our side is 1, 2, 3 and 4. One for I, one for minimum, one for j, and one temporary variable for exchanging two numbers. So now we have 4 extra variables, and if we have any input size, the number of variable will remain same as 4. So the space complexity of this algorithm can be written as theta 1, because 4 is constant and constant time is represented as any notation enclosed by 1. Since there is no best case and there is no worst case, there is only one case, so this is represented in the theta notation.